I have a piecewise defined function. F of x is equal to 1 over the square root of x between 0 and 1, including 1, and 1 over x squared for all the x's greater than 1. And so I have that graphed here, and we see this spot here where our function's not differentiable, but nicely it is continuous from 0 to infinity. Right? If I think about plugging a 1 into this, I'll get 1. If I think about plugging a 1 into that, I'll also get a 1. The limits from the left-hand and right-hand side equal to each other, and the function is defined at that point. So we have a function that's nice, happy, and continuous. So I think this integral does exist. Because it is defined in the way that it is as a piecewise defined function, I do think it's pretty natural to think of splitting this up into two integrals. The integral from 0 to 1 of f of x plus the integral from 1 to infinity. Because what that actually lets me do is on the interval between 0 and 1, my function is just equal to 1 over root x. And on the interval between 1 and infinity, my function is simply 1 over x squared. So what I have here are two integrals, both of which are improper integrals. This first one's improper in that way of a type 2 because I have a vertical asymptote at its lower bound. This is a type 1 improper integral here in blue because I have an infinity in one of my bounds. So I would like to evaluate these two improper integrals and find the value of this very improper integral. So first things first, I'm going to rewrite this first integral with a limit as a approaches 0 from the right-hand side. A goes in my lower bound. Instead of 1 over root x, I'm going to think about that as an x to the minus 1/2. And to that, I'm going to add, and I need to think of a limit now as b approaches infinity, 1 to b, and x to the minus second dx, 1 over x squared being the same thing as that, x to the minus second. I have two antiderivatives to find and then two limits to evaluate. Let's see what happens. Add 1 to the exponent, divide by the new exponent, and evaluate from a to 1. And then finally, the limit as b approaches infinity, and do the same thing. I actually end up with a minus 1 over x, evaluated from 1 to b. Plug in a 1 first, we'll get out a 2. Minus what happens when I plug in an a, I get 2 root a. Plus a limit as b approaches infinity, minus 1 over b, minus a minus 1, so a plus 1 there. Let's take our two limits. The limit as a approaches 0 from the right, that part goes away and I just get a 2. As b goes to infinity, this part goes away and I just get a 1. 2 plus 1 is, well, 3. To me, what's really cool about that, if I shade all of the area to the right of the y-axis, everything under this curve, I get exactly 3, or I get an area that converges to 3, a little better said. Here in blue, we're really talking about what this area converges to. And in orange, we're getting what all of this area converges to. But what I would like to point out now is that this blue area and this orange area look to be the same. And the reason I say that is because these two graphs are symmetric over the line. Two graphs right now, I'm thinking about the 1 over root x side and the 1 over x squared side. It's really just one function. But those two parts are symmetric over the line y equals x. This function is its own inverse. If I fold my graph over that dotted line, the orange part lays right over top of the blue part, or actually this way. The blue part lays over the orange part. and the same thing here. So I think the blue area and the orange area have the same value. Well, I know the blue one worked out to 1. The orange one here then works out to 1, and then the only thing I haven't shaded yet is this square, this 1 by 1 square. And so if I put all of that together in orange, up here I've shaded 1, the 1 by 1 square, and then the one more for the bit shaded in blue, and we still get 3. I'd only ever approach this kind of doing what we did here, but there is some nice symmetry going on.